Hi everyone. So today we'll be talking about alternating series. And well, let's start with the definition, right? So an alternating series is a series, about that, a series whose terms alternate between being positive and negative. So as opposed to most series we've been studying, you can actually have negative, you have to have negative terms in these kind of series. So for example, one of the most important alternating series is 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 plus dot dot dot. So this is called the harmonic alternating series, and you can use some very neat math to show that this actually converges to ln of 2. Anyway, another more basic example is 1 minus 1/4 plus 1/9 minus 1/6 plus 1/25 plus dot dot dot. And we can just rewrite this as the sum from n is equal to 1 to infinity of -1 to the n plus 1 times 1 over n squared. And lastly, well, note that in the definition, we did not require the first term to be positive, right? So we can just start with a negative number and then add a positive one, and then subtract something, add something, and so on and so forth. So, for example, -1 plus 1/8 minus 1/27 plus 1/64 minus 1/25 plus dot dot dot. This can just be written as the sum from n is equal to 1 to infinity of -1 to the n times 1 over n cubed. So as you can see in these two examples, an alternating series takes one of these two forms. So sum from n is equal to 1 to infinity of -1 to the n plus 1 bn, where bn, we're going to see later that we kind of require bn to be positive, or the sum from n is equal to 1 to infinity of -1 to the n times bn, where bn again is positive. So we've studied so many series tests so far, right? We've had the comparison tests. We will be talking about the ratio test in a bit. We've had the p-series test, the integration test. So let's talk about the alternating series test, the ACT. AST, sorry, not ACT. So an alternating series of the form of one of the two above forms. So sum from n is equal to 1 to infinity of -1 to n to the n plus 1 times bn, or sum from n is equal to 1 to infinity of -1 to the n times bn converges if, well, two conditions are satisfied. So first, all the bn's must be positive. So 0 is less than or equal to bn plus 1, and the bn's are decreasing. So 0 is less than or equal to bn plus 1, which in turn is less than or equal to bn for all n greater or equal than 1. And not only are the bn's decreasing, their limit is actually 0. So the limit as n goes to infinity of bn is actually 0. Okay. So this is the alternating series test, and we'll use this a lot this week. And you're probably going to use it in one of your FAs. So now, a very, I guess, one of the first questions you could ask yourself as well, what if we have an alternating series, and how can we see if an alternating series converges other than this theorem? A very basic theorem says that, well, if the sum of the absolute values converges, so does the sum of the an's. So again, if the sum from n is equal to 1 to infinity of the absolute value of an converges, so does the sum from n is equal to 1 to infinity of an. And here you could see a failed attempt of me trying to prove this. I fake proved this. Anyway, so, well, this theorem kind of motivates the next definition we're going to have, and this is the last definition I will cover in this video. So, definition. Okay. If the sum from n is equal to 1 to infinity of the absolute values of an converges, we say that the series sum from n is equal to 1 to infinity of an converges absolutely. Converges absolutely. Okay. In contrast to this, well, let's say that, so this theorem is not an if and only if theorem. So if the sum from n is equal to 1 to infinity of an converges, this does not mean that the sum of the absolute values converges. Anyway, if the sum from n is equal to 1 to infinity of an converges, but the sum from n is equal to 1 to infinity of the absolute values of an diverges, we say that the series sum from n is equal to 1 to infinity of an converges conditional. And throughout this week, we're going to do a lot of exercises regarding all these definitions. And I hope you've enjoyed this video, and I hope you will enjoy the rest of your Cognitive experience.